Hello there, and welcome to a brand new video series launched by me, Geology Professor Shawn Willsey. This is the Geology 101 Physical Geology video series, and this is episode 1, or the first lecture. This is an excellent place to begin if you're looking to understand some geology basics, concepts, if maybe you're new to geology completely, or if perhaps you've had some geology education in previously and you're just looking for a refresher. So thanks for joining me. This course and this lecture series is completely modeled after the college course I teach. I'm using the same slides. I'm using by and large all the same materials, and everything's pretty much the same. The only thing missing from this course that you would otherwise be getting in a traditional college course would be, of course, the lab experiences, rock and mineral identification, field trips, and other applications that we might do in a lab setting. But other than that, this has all the same material. You can also use a lot of my existing videos on my YouTube channel to find specific videos and topics that might supplement the material that we present here. So let's go ahead and get started. This is our first episode. This is what I'd like to call Introduction to Earth, kind of introducing the subject of geology, why it's important, and then getting into a basic model for the interior of the Earth that will help us in the next few lectures where we start talking about plate tectonics, one of the most fundamental concepts in all of geology, which really dictates and governs how so much of our planet behaves. So just some fun little eye-catching photos here at the beginning just to show the relevance of geology, some of the hazards that geology poses. This is along the rim trail here in Twin Falls after a large rainstorm and some mass wasting, sliding along the canyon rim. This is the interior crater of Mount St. Helens here on the right. When it was erupting in 2006 when I was up on the summit. So this is actually lava, even though it's not glowing incandescent. This is a stickier, pastier type of lava. Of course, obviously lava here on the lower right in Hawaii with a former student. And this is just a fun photo down along the Utah-Arizona border with some balanced rocks there showing the effects of differential weathering. Geology as a science is looking at how the planet works, just understanding our planet, what processes govern our planet, how it behaves, and what it's made out of. And there's really two main courses I teach here at the college with respect to geology. This course, of course, is Geology 101, Physical Geology, where we're going to look at what the Earth is made out of, rocks and minerals, and then also the processes that dominate and govern the planet. So the different processes, both internal and external, that really shape our planet. And so this is a great place to start if you haven't had any geology class. It's the class I recommend to people take at the beginning of their geology educational pursuits, is to take this class so that they can then build upon that knowledge with subsequent courses. Another course I teach here at the college is Historical Geology, which basically studies the Earth's evolution over time. So it looks at things like fossils, extinction events, how plate tectonics has shaped the landscape, mountain building events. It's an incredibly fun course. I may at some point put together a video series on that, but I'm going to focus on this 101 series first. So those are just two aspects of geology. And then I always like to start any class or survey of any subject with sort of the who cares question, like why is this relevant to me? How is this going to impact my life, make me a better person? And so let's look at a few reasons why geology is worth considering and studying as citizens of this planet. So the first thing that comes to mind might be geologic hazards. So different events and things that happen naturally within our planet or at the surface that impact humanity. So that could be things like earthquakes. In this top left photo, we can see some of the devastating impacts from an earthquake in Haiti in 2021 and the buildings that had toppled there. At the lower left here, we see an eruption in Iceland, and the volcanic eruption has produced, in this case, lava flows that have poured down the slope and are taking out a few homes there. Or it could be, as in the case with the upper right one, something like a mass wasting event. A section of the Snake River Canyon here locally has collapsed down and formed this debris fan down into the Snake River. And so whenever we think about these geologic hazards, we like to know why they occur in certain places, why are earthquakes more common in some regions versus others. Same with volcanic eruptions. So not just the where things are spatially, but also why they occur, what the underlying processes are. We like to understand, the frequency in which these events take place, and then also their magnitude, how big they are, and then of course how they impact humanity. And so we'll touch on all these subjects throughout this course. We'll spend some time on earthquakes, we'll look at volcanic eruptions, we'll look at mass wasting, flooding, tsunami, all sorts of things that you've heard about in the news that oftentimes adversely impact the human existence here on planet Earth. Another reason geology is pivotal and important to humanity is it provides a lot of the natural resources that we use for our way of life. That could be anything from minerals, here's like a salt plain in Death Valley, like a playa, this dry lake precipitating out salt, which we use for a variety of purposes. Could be water and how we harness water and use it both for ourselves and drinking water, but also for irrigation, for generating electricity, for other reasons, and then also looking at different energies and fuels that we extract from the earth. So oil and gas, coal, those sorts of things. So our way of life is largely predicated on the ability we're able to use the abundant natural resources that the earth provides and then put those to good use to make our lives and our quality of life much better. So this is pretty pivotal, especially in the Western United States. Things like water and energy, these are important issues. And so we'll touch on those to some degree. Another reason that geology is important is it helps understand our past. So this might be something that we get into a little bit more with the historical geology lecture series, but this topic here, we understand Earth's past and the life history of the planet through the rock record. So by studying that rock record and the fossils therein, we can get not complete, but as close as we can, a very comprehensive overview of the different events that have happened in Earth's past. Of course, by studying the history of the Earth, that might give us a sense for what things might take place in the future. So it benefits us in many ways looking at Earth's history and putting together those pieces, those clues, if you will, and putting that all together. Fundamentally, this is the one that in my classes I tend to spend a little bit more time on because I think it's the one that'll more directly impact the students no matter what career path or vocation they choose. And that is just property and buying property and making good decisions. So you can see a couple photos here. The bottom one on the left there is a lava flow about to pour into this pool. This is in the Canary Islands area. I didn't put dates on these, but this was, I think, in 2022 or 2023. Top left is some flooding and river erosion that's undercut the foundation of this home. And then my favorite one here is this one in the upper right from Florida. So you can see this home that's completely collapsed into this sinkhole. And the photo just says it all. And then there's this yellow tape that is surrounding not just the collapsed home, but the one next door. And so if we read between the lines and make an interpretation, it looks like what's happening here is both properties have been condemned by either the city or the county or some other jurisdiction. We can see the moving van outside of the home that's still standing, and they usually have, maybe 24, 48 hours to get all their belongings packed up in the moving van and vacate. So situations like this are real. They occur in different areas, not just in the U.S., but worldwide. And so by understanding geology better, we can make better and more informed decisions about where we buy property, what homes we purchase, looking at landscapes and what hazards might exist there. And then maybe hopefully making good decisions about ourselves and our investments and our property. So we'll spend some time looking at those, especially in the context of flooding, mass wasting, maybe even earthquakes and volcanoes as well. So let's go ahead with that overview and giving you a little bit of reasons why geology is important. Let's look at the interior of our planet. Now, I'm about to present to you a model for what the planet looks like on the inside, but let's make sure that we realize no one's been there, that we have not been to the center of our planet. So even though it's a long ways away, we can actually infer quite a bit about the interior of our planet. And so looking at Earth's history through the rock record, we know that early in Earth's history is quite molten, as were the other planets in our solar system. And the more dense elements tended to gravitationally collapse and sink towards the center, and the lighter elements were closer to the surface. So that set up a situation where our planet became layered, or it started to accumulate different compositions at different depths, and so it set up a layered planet, which makes us it makes it incredibly important for our planet that we have a layered interior. And so when you think about the planet's interior, I want you to think of an apple, which is a pretty good stand-in terms of proportion and scale for the layers that we find on planet Earth. And so the first one to think about when you think about an apple is think about the exterior. And so we think about the exterior of the apple, and we typically call that the skin of the apple, or the peel, I suppose. And that's analogous to the Earth's crust. Now, how much of the apple's area is covered by the skin? Well, it's pretty much all of it, right? Except for the little stem here at the top and the little counterpart there at the bottom. Near the entire surface of the apple is covered by its skin. But in terms of the apple's volume, once you take a bite of the apple and get to the interior, the skin is quite thin, and it represents only a small portion of the entire volume of the apple. So once we get through the skin of the apple, again, which is just like the Earth's crust, then we enter the next region of the apple, which is much thicker. And I guess, I don't know if there's a good name for it, what the interior of the apple is called, the fruity part, the fleshy part, the meat of the apple, but that would be analogous to the Earth's mantle. And volumetrically, that represents a much bigger part of both the apple and the Earth. So this is this is what most of the apple is made of, is this layer or this substance within the apple. And accordingly, that's what we have with the Earth, is this layer called the mantle. If you get to the middle of the apple, that's of course the core. And we have a similar layer in the Earth that also is called the core. And so we end up in a simple way with this very simplified diagram here, where we have the crust on the exterior, the mantle, which represents the bulk of the volume as opposed to the other layers, and then the core of the Earth at the very center of the Earth. We know through various measurements and studies that as you descend into the Earth, it gets hotter, the pressures increase, and also the density increases as well. So the rocks become much more dense as you descend into planet Earth. So let's go through each one of these layers one at a time. And let's start with the core. We won't spend a ton of time with the core, and there's limited evidence we have about the core because we haven't actually directly sampled it, but we can infer some information about the Earth's interior. And I'll get to, you might be asking at this point, like, how do we know all this? Where is this information coming from? And I'll just let that ride for now, and I'll circle back to that here in a bit. So we know it's quite hot in the interior of the planet. There's a lot of heat that's still generated there. We have heat that's left over from all these planetary fragments and comets and asteroids coming together early in the solar system's history. There's also heat in the interior of the planet that's generated by radioactive decay, which we'll talk about later in the video series. So it's quite hot. Even though we've been losing heat for 4.5 billion years, we still have an incredibly hot interior. And we know, based on modeling the substances at the temperatures and pressures in the interior of the Earth, that the Earth has a solid inner core and it's surrounded by a liquid outer core. And again, I'll get to some of the evidence for that here in a bit. We think it's mostly iron, and so the iron in the liquid outer core is able to move and fluctuate and flow a little bit, and it's believed that that movement of that liquid iron generates Earth's magnetic field. And so we have not only this solid and liquid cores and this iron-rich interior, but it actually generates a magnetic field. So when you pull out your compass, it points to the magnetic poles. So a little bit about the core, but not a lot that's relevant to us here geologically, because we're going to focus on the next two layers in a lot more detail. So I've drawn here a very simple diagram. Hopefully this is helpful. And this is not to scale, but from the surface down to the center of the Earth, how far is that? What kind of distances or lengths are we talking about? It's a little under 4,000 miles or a little more than 6,000 kilometers from the surface down to the center of the Earth. We've talked about the inner core and the outer core. But then we enter the mantle, and the mantle actually has some interior layering within it as well. So let's start from the middle or the lowermost layers and work our way up towards the surface. So we have the lower mantle, which is solid and strong. It's still, dense rock, but if someone dropped a chunk of the lower mantle onto your foot, you might break your toe. It's dense, solid rock. Then we have this layer here that's going to turn out to be quite important as we get into plate tectonics in future lectures, called the asthenosphere. And the asthenosphere, I want you to think of it as it's still solid, but it's very weak and soft. It flows, it deforms a little bit, but it's not true liquid. It's also not truly magma itself, but it's a layer whereby if certain forces are acting upon the asthenosphere. If you do the right thing to the asthenosphere, you can generate magma. So this is a place where a lot of magma is generated inside the planet, is within the asthenosphere, depending on what you do with it in terms of pressure, temperature, and even water content, as we'll get to when we talk about plate tectonics. So this is it's a soft, squishy layer, and this is essentially the layer that the plates, and we'll talk about tectonic plates more in the future, are riding upon. This allows our planet to have chunks of rigid rock that can move independent of each other. They're all riding on this soft, squishy layer we call the asthenosphere. And then sitting above that is the upper mantle, which is again solid, strong rock. A lot of times we combine the upper mantle with the crust, whether it's ocean or continental crust, and we call that the lithosphere. So the plates themselves, the things that are moving around and colliding and causing earthquakes and volcanoes in many locations, those are the lithospheric plates. So lithosphere refers to both of these layers collectively, and it's all sitting on top of the soft, squishy, weak layer called the asthenosphere. So this is an overview of the mantle, and this is a good place to maybe pause the video and make sure you take some notes or make sure you understand this because this will be important moving forward. We'll stick with my diagram here as we go to the next layer, and that is the crust. Notice that the way I've drawn the crust here, it shows it both as a thin layer over here beneath the oceans, and then as we move onto the land, the continents, it's much thicker. And so we do have two types of crust on planet Earth in our solid outer layer. Remember, this is just like the peel of the apple. And we have continental crust, which is quite thick. I put this in miles here. You can convert that to kilometers. I'll have to do that in future episodes. Keep it in both units. 25 to 40 miles thick. That would be probably 35 to 60 or 70 kilometers thick. And this contains a lot of low density material. So a lot of silicon, oxygen, aluminum, potassium, sodium. And the main rock that makes up the continental crust is a rock that looks like this. This is a piece of granite. So you can see it's mostly light colored, but it does have a few dark colored flecks in it in places. So this is a chunk of continental crust. So if you were to dig down deep enough beneath the continents, any continent, in most locations you would run into literally miles and miles or kilometers and kilometers of this type of material, this material called granite. It may not look like the granite countertops in your house because countertops are not always following geology convention, but this is the type of material here, is granite. So there's our first rock, granite. And then to contrast that, we have the layer underneath the oceans. Now the crust here is a lot thinner. It's only a few miles or kilometers thick. It contains much more dense material, and like iron, magnesium, calcium. And so this is actually a rock we call basalt. And here's what basalt looks like. It's very dark. You might be able to pick out some of the little holes in here. This is what a lot of folks would call a lava rock, and it is. This was lava when it erupted, but this is also known as basalt. So this is what sits underneath the oceans on the ocean floors. If you were to scuba dive down to the ocean floor and push away all the mud and the fish poop and the muck, you would get down to some layer of basalt. And the reason we have the oceans where we do on planet Earth is because this rock is so much more dense than this one. Okay, so even though as I feel them in my hand, they just kind of feel like rocks, but if you took an equal volume of each of these, this one is heavier, it's more dense. And the density difference is pretty significant. And this material is so dense that it causes the crust to sit lower on the surface. So it pushes down, it sinks lower at the surface. And that's why we have the oceans where they do, is the water running off of the buoyant continents is pooling up in these vast areas of the ocean crust and forming the Earth's oceans. So the Earth's oceans are where they are because that's where the lowest rock is sitting. It's kind of like if you get a rainstorm in your yard, you might have a few places in your yard where the grass and your property is a little bit lower, and maybe the water ponds in that area, or if you run the sprinklers too long, you can get a little bit of ponding because it's the lowest point. And that's the same with the oceans. They are the lowest point on the planet because they are underlain by this dense, heavy material called the oceanic crust. So important differences there, and we'll circle back to those here in a second. Oh, right here. Here we're going to circle back to them right now. So the two big differences, or a couple big differences between the crust, we've talked about the density. So things just to remember, just a couple highlighted points that you can keep in your memory bank, is that oceanic crust is significantly more dense than continental crust. Continental crust is buoyant. That's why it is the land. Ocean crust is dense. That's why it forms the area underneath the oceans. Continental crust tends to be a lot older. It's not always true, but it's generally true because the ocean crust, as we'll see once we get to plate tectonics, it gets recycled. We don't have a lot of very old ocean crust on planet Earth. But continental crust, because it's buoyant and it resists getting destroyed by plate tectonic processes, it tends to endure for not just millions but billions of years, and it can persist for long periods of time. And then the other big difference here between the two types of crust is, as you can see, the continental crust is much thicker. So it's thicker, but it's low density, and so it's more buoyant than the ocean crust. Okay, so some big differences there with the ocean crust. I told you I'd explain, excuse me, where the evidence came from for all this knowledge, because realize no one's been to, the center of the Earth. We haven't even penetrated nearly this far. And let's see how far we've actually gone. So we've got a radius down to the center. And again, I apologize to everyone that I put these in miles. I need to start transitioning some of these to kilometers in the metric system. But the Earth's radius is about 4,000 miles, 6,300 or so kilometers. The deepest mines on planet Earth go down about 2.5 miles, so about 4 or so kilometers. The deepest drilled holes that we've actually been able to drill a borehole down into the planet is about 8 miles, which would be like maybe 14 or 13 kilometers. And so the point here is that with all our technology and all our advances, we have only been able to directly sample, directly access the Earth's interior a minuscule amount of the full distance to the center of the Earth. And so where does our evidence come from? Well, it doesn't come from any direct methods. It has to come from indirect data. And the analogy I like to use in class is, imagine if you've got something in your body that hurts, right? Like, oh, I've got this severe abdominal pain. Of course, nowadays, what we'll do is we go to the doctor, and what are they going to do to figure out what's wrong with your abdominal cavity? They might take an X-ray, they might do MRIs, they could do all sorts of different imaging techniques to see what's going on inside you without directly accessing it, with instruments. Maybe in the dark ages of medicine, they might cut you open and see what was in your causing the problem. But nowadays, we use imaging to detect what's going on there. And in a similar fashion, we can actually detect or image the interior of the Earth by using earthquakes, by using energy waves that pass through the planet. Sometimes they bounce back and reflect, sometimes they change direction and refract, but by studying the behavior of these energy waves, which happen all the time, earthquakes are always going on planet Earth, that provides us a tremendous amount of data, but recognize it's indirect data. We're just looking at how those waves of energy pass through the planet, and then interpreting what those mean. So if we had a planet that was all the same, right? So if planet Earth was just one big rock of uniform composition, uniform material all the way through, then what we would expect is if there was an earthquake, that the waves would pass through the planet at the same velocity without changing direction, and they would be detected in other parts of the world, right? So that's what we would expect if the Earth was just one big, boring rock. But that's not what we see, thankfully. What we see is something like this. We see earthquakes being generated, and as those seismic waves pass through the Earth, they sometimes change direction. So you can see these little black lines here actually changing direction slightly. This is called refraction. In the case of these red lines here, which are S waves, and we'll get to earthquakes later on in a future video episode, notice that those S waves don't even go through this layer of the Earth, which is the outer core. They aren't detected anywhere on the opposite side of the planet. There's actually a shadow zone where the S waves are not detected. And so it's by analyzing all these earthquakes that have happened on planet Earth, based together with other evidence we have, that we're able to put together this interior model and this image of what the Earth's interior looks like. So hopefully that's a good overview of the Earth's interior and what it's like. We'll circle back to many of these concepts in the next couple of video series as we talk about plate tectonics. It's imperative that we understand the differences in crust and also parts of the mantle as we start talking about plate tectonics. So make sure you feel good about that material before you move on. And then the last little thing we'll get to here as it relates to geology is our concept of time has got to change. Our concept of time as humans is not helpful in understanding our planet. Our concept of time is seconds, minutes, hours, days, weeks, months, years, decades, maybe centuries, when we think about history, human history. And that's kind of about as far as we can wrap our minds around. If a good long life would be a 100-year lifespan, which feels like a long time from a human perspective. But from the perspective of the Earth, the 100 years is nothing. It is literally a flash in the pan. It is not that significant. So in geology, we talk about things taking millions of years, maybe hundreds of millions of years, sometimes billions of years, and we throw around these millions of year time increments like they were just loose change. Like, oh yeah, that was only 3 million years ago. It's pretty recent. And so it's a different concept of time than maybe what you're used to. A lot of our geologic processes are quite slow. So they're at like micrometers per year or centimeters per year. They're, not moving at very rapid rates. But what we have to make these processes significant, even though they're only moving a small distance per year, is we have lots of years. And if you have lots of years, a small distance can add up to a much bigger distance given enough time. And so we see that there's a lot of geologic events that are kind of slow, but there's also some that are kind of fast. And so we've got this interesting juxtaposition of slow, steady, somewhat boring, snail's pace type of geologic processes. Maybe something like even mountain building can be dramatic at times. Maybe something like glacial movement can be maybe slow or feel slow. The movement of the plates, of course, can seem quite slow. But then we also have recognized over time that there are these sudden dramatic events that occur on Earth that radically transform sometimes life and extinction events, but also just the course of events taking place. And so that's a concept that just be ready to struggle with it, because our concept of time is so much skewed to the human experience. But hopefully as you study geology a little bit more, you'll be able to broaden that time scale in your brain and think about things in thousands and in millions and in tens and hundreds of millions and even billions of years as we move forward. And so we see some things that are quite quick, or excuse me, quite slow to take shape. This is Boar Peak in Idaho. This is the tallest point in Idaho. Some lovely banded sedimentary rocks up there. But this mountain took tens of millions of years to form, and it took earthquakes. There's actually a fault scarp. This line along the bottom of the mountain frontier is a place where in 1983 there was a magnitude, what was it, almost a 7 earthquake, and the mountain was pushed up about 3 feet. The valley was dropped down about 7 feet for a total displacement of about 10 feet. So that was a dramatic movement in one day. But then typically what happens with these mountains is, many hundreds or thousands of years go by till the next event. So it's kind of episodic, but it took millions of years of uplift for this mountain, this lofty mountain range to form. And up at the top of this mountain is limestone. These are actually rocks that were deposited at the bottom of the ocean. So literally things that were once low, like the seafloor sediments and the fossils that are found there, are now high. And that's the dynamic nature of some of these processes we're going to be looking at. So some things take a long time to form, and other things are very rapid. This is Meteor Crater in Arizona, where a good, I think, football field size or so rock fell out of space, punctured a big hole in the northern Arizona desert, and formed this large crater. And we even have evidence of much larger craters than this one now in Earth's history. So some things are slow, some things are quick. Both processes are operating, and we have to take that into account as we look at geology and look at how this planet works. So that is lecture number 1. Hope you've enjoyed it. The nice thing about these videos is you can digest them in chunks. You can pause, rewatch, whatever you want to do. But hopefully you've enjoyed this and you will enjoy the rest of this video series. We'll get into plate tectonics next, and we'll start with that because that's a good way to understand fundamentally what happens inside the planet and how it shapes the Earth's exterior. And then we'll get into other geologic processes as well. So thanks again for your time. Thank you for supporting this channel and our geology education efforts, and good day.